Hello children, again we will start here some more problems of continuity which are of different kinds. I'll take the exercise 5.1 again and I start with the question number 16. Here a function is given as such. Now if I compare with the other kind of problems given in the exercise earlier, I can see here there are 3 points. I can see at 3 different definitions are given. So if I watch it constantly, I can see, if I observe it, I can see that -1 and at point 1. So in this case there are 2 critical points. What are these critical points? These are -1 and 1. So in such kind of questions we need to check the continuity at 2 different points. So we'll check the continuity at 2 different points, and first we'll take x equal to -1 and I see f minus 1 is equal to -2, and then I take the limit left hand limit of the function at x equal to -1, and I keep there the limit, left limit. So limit x tends to -1 negative fx, and using this again I see here I keep x equal to -1 minus h, and if x tends to -1, h tends to 0. Keeping this, I get on the function limit h tends to 0 f -1 minus h, and that gives me -2 because it is less than -1. So that gives me value -2. I take on to right hand limit. Again I take limit x tends to -1 plus fx, which gives me, keeping x equal to -1 plus h, and that all the way I see that my right hand limit is also coming -2. From all the 3 values, left hand limit, right hand limit, and functions value at -1, we see that the value comes out to be -2. Hence we can see that function is continuous at x equal to -1. Now I need to check the continuity at the other point also, and that was x equal to 1. First I find the value of the function at 1. It comes out to be 2. Then I take on to left hand limit, and left hand limit I see that limit x tend to 1 minus fx, and keeping 1 minus h as x, and I find that left hand limit comes out to be 2. And then right hand limit the same way, it comes out to be 2 again, and I check here my left hand limit, right hand limit, and functions value at the point 1 is 2. So at this point a function is continuous at this point, and here since 2 critical points were given, but at the point -1 as well as at the point 1 the function is continuous, so we can write the statement that there is no point of discontinuity at all. Fine. Now I'll take the question number 19, which is a very important question, and it is a combination of 2 functions. One function is a simple polynomial function and the other function is a greatest integer function. So for that we need to check the continuity. So since we are just asked in general check the continuity, since it is a real number, so in general we suppose that for any x equal to c, where c is an integer value, so it is asked that for all integral value check that it is discontinuous, check the continuity. So we just see that let c is a integer, and what is the left hand limit? Left hand limit comes out to be x tending to c negative gx, and let c equal to c, x equal to c minus h. If x tends to c, h will tend to 0. Again, by keeping this x equal to c minus h, I put the value here. Limit h tends to 0. It was x minus inside the bracket x, so it has become now c minus h minus c minus h. Now here it is a polynomial function, but here we need to understand that it is a greatest integer function which takes the value of the equal or the value of the left side of the integer. Now again, if I have drawn a graph here, if c is a point here, then c minus h will lie on the left side of c, somewhere here. And when it lie on the left side of the c, so we will write, when the bracket will be taken out, the left side integer value is written. So when the brackets are open, it will be written as c minus 1, as c minus 1 is the integer on the left side. So on solving this, we get the value comes out to be 1. Now for right hand limit, again x tends to c plus gx. If we keep x equal to c plus h, then we see that right hand limit comes out to be limit h tending to 0, c plus h minus inside the bracket c plus h. Again, just observe this graph. It is c plus h on the right side of c. And when the bracket is open, it takes the value of the integer lying on the left side. So c plus h will come somewhere here and the left side integer will be c. So when the bracket will be open, it will come out as c, and while keeping the limit, I can see that it is coming 0. So it's clear now that left hand limit is not equal to right hand limit. Hence, the given function gx is not continuous at x equal to c, or gx is a discontinuous function at all the integral value. Now question number 20, it is the function fx equal to x square minus sin x plus 5. So we are asked, is the function continuous at x equal to pi? First we will try to find the value of the function at the point pi. So it comes out to be pi square plus 5. Now trying to find the left hand limit. So for that we write here x limit x tending to pi minus fx, and we keep x equal to pi minus h. When x tends to pi, h tends to 0. This way I write limit h tending to 0 pi minus h, which gives me, by keeping the value of the function here, x square minus sin x plus 5, which gives me here on place of x it is pi minus h square, minus sin of x it was pi minus h become now, and plus 5, which after opening limit h tends to 0 pi square h square, and this way I opened it, the identity. This is minus 2 pi h minus, I use the formula here, sin pi minus theta is sin theta, so minus sin h plus 5, and after keeping the limit here I get the value pi square plus 5. Now finding RHL. So for finding the RHL, the same way I write x equal to pi plus h, and I keep the same way and I open it using identity, and since pi plus h will give me minus sin h, so this here comes the minus and minus multiplied together gives me plus sin h plus 5, and again by keeping the limit I get this value pi square plus 5 because sin 0 is 0. So in this particular case, since my LHL is equal to RHL and it is the same as the value of the function at pi, which is pi square plus 5. So hence the given function is continuous at x equals to 5. Now some again different kind of problem, that is finding the value. Already if a function is given continuous, then we need to find the value of some unknown number. So in this question number 26, find the value of k if fx is continuous. It is first it is given that continuous only, and then we have to find the value of unknown k here. It is the question number 26, exercise 5.1. So fx is this function. So first we'll find f pi by 2. f pi by 2 is given 3. So for that I don't need to find RHL because f pi by 2 is here and only finding since the function is continuous. So only my purpose will be solved if I find only the left hand limit. So left hand limit at x is equal to pi by 2 can be obtained as limit x tending to pi by 2 negative of fx, and keeping x equal to pi by 2 minus h, I find the left hand limit this way. I keep the value here in the given function and solve it, and I see here limit h tending to 0 pi k sine h, because cos pi by 2 minus h will give me sine h and upon 2h, and that on solving gives me, I just k by 2 I take it out and apply the limit here h tending to 0 sine h upon h, which is equal to 1. So it comes out to be k by 2. Since the function is continuous at x equal to pi by 2, so left hand limit will be equal to f of pi by 2. On solving this has come out k by 2 equals to 3. On solving it gives me the value k equals to 6. Now there are some problems based on the composition of function. We need to understand what is the composition of function. If fx and gx are the two functions and both are continuous at point x equal to c, then FOG or GOF are also continuous at x equal to c. What is FOG here? That is f of gx, and GOF is g of fx. Again a question is there, and that I try to explain you through composition, and this is again a question from the same exercise, that check the continuity of this function, and I clearly see that it is a composition of two functions. One function is cos x and the other function is x square. So my function is given fx equal to cos x square. So I suppose let gx equal to cos x and hx equal to x square. I can clearly see that fx equal to g of hx. So this way if I write g of hx, so that means hx was x square, so g of x square, which will give me cos of x square. And I can see since hx equal to x square, which is a polynomial function, hence it is a continuous function. And then gx equal to cos x, again it is a continuous function. Therefore g of h, that is fx, which is equal to cos x square, will also be a continuous function. Hope you have understood the problems, how to solve the problems based on composition of functions. Now the very important question here I would like to take, that is question number 34. Again I can say that it is on the combination, based on the combination of two functions, and this question says find all the points of discontinuity of f defined by fx equal to mod x minus mod of x plus 1. That's a very important question. Now I can see here it is one function, however both are mod function, but it is one function and it is another function. So let gx equal to mod x and let hx equal to mod of x plus 1, so that fx is equal to gx minus hx. Now using the definition of mod, I know that gx equal to mod x, if it is, the mod definition says it is equal to minus x if x is less than 0. It is equal to plus x if x is greater or equal to 0. And if I apply the same definition here in the hx, it says hx equal to mod of x plus 1, which implies minus of x plus 1 if x plus 1 is less than 0. That means if x is less than minus 1. Minus 1 is taken to the right side, and it is equal to x plus 1 if x plus 1 is greater or equal to 0, or x equal to greater or equal to minus 1. Now I tried to define the function in a more appropriate way by drawing this. Since here I am getting the two critical point, one is 0 and one is minus 1, and my function is a combined function, so I need to describe it. So I take the values on the number line as 0 and minus 1. On combining, I can see that function is equal to gx minus hx. I see here, if I take the value less than minus 1, if I take the value less than minus 1, so my first function is less than minus 1 will come, because less than 0 is minus x, and the other one minus of, it is less than minus 1, minus of minus x plus 1, this way. Then I come to the values between 0 and minus 1. Between this interval, for this interval I see my function, if it is less than 0, so again less than 0, it is less than 0 for this function, so it will come minus x, and for this it is less than 0, so for less than 0 it will come x plus 1. So it is hx is minus x become now, and it is minus of x plus 1, and I write it here x greater or equal to minus 1 for this interval, and it is less than 0. Now for the third part, this is the values after 0. For this is greater than 0, this gives me x, and after 0 also, from this I see this gives me x plus 1. So this is x minus x plus 1 now, x is greater or equal to 0. Again I calculate all this and define the function here again, which gives me minus 1 after solving this. When x is less than minus 1, the function becomes minus 2x minus 1 when x is lying between minus 1 and 0, and it gives me minus 1 if x is greater than 0. Now this way I have defined my function. Now the very important part, that I need to check the continuity at the 2 points which are minus 1 and 0. So at x equal to minus 1, I check the left hand limit, and left hand limit comes to 1, and at right hand limit again I check for right hand limit, it comes out to be 1 again, and the value of the function at minus 1, I keep this value and it comes out to be 1. So it's very clear that my function is continuous at x equal to minus 1. Now at x equal to 0, the other critical point, left hand limit is minus 1, and the right hand limit is also minus 1, and the value of the function at point 0 is also minus 1. So at this point I can see that the function is continuous. So however, we can say that we can come to the conclusion that the given function fx equal to mod x minus mod of x plus 1 is a continuous function for all values. Hope you have understood the complex problems of continuity as well today.